Today in this video, we're going to be starting out with our first conic section, and that is of the parabola. And we're going to go through the different characteristics of the parabola. Now, I want to kind of give you a heads up here. I know when I bring this up, I've got a lot of students that go, well, I know all about parabolas. We've done lots of stuff with parabolas before, and we've solved parabolas using quadratic formula and things like that. When you talk about conic sections, though, the conversation about parabolas is quite different than it is when you're going through solving quadratics and you talk about parabolas at those points. In this section, we're going to be interested in some of the properties that parabolas have, which you might never have thought about that, the fact that there's properties, and because of those properties, there's some different applications to that. And so in this case, when we're solving, we're not necessarily solving for, in the past, you would have been looking for the x-intercepts. We're going to be solving a lot of times for what's called a focal point, which is not something you would have discussed ever before. So please don't make an assumption that you know all about this, because this is going to be quite a bit different than conversations about the parabola in the past. First of all, it is one of our what are called conic sections. If you take a cone and slice it, there's different shapes that you can get. It depends upon the way that you slice it. Let's say you just go straight across and you look at what's left right there. Well, of course, that's going to be a circle. If you sliced at an angle like this, where I went through both sides of the cone, but it was at an angle, that's going to be what's called an ellipse. If we slice through, we're going through a side, but then the bottom, not perpendicular to the bottom, that gives us a parabola. And if we slice through a side to the bottom where it is perpendicular to the bottom, that shape is going to be a hyperbola. And these are our different conic sections. Now, honestly, a point and a line are technically conic sections because it's something you can get out of a cone, but nobody usually talks about them. They're just not, in this context, used quite in the same way as what we're going through. So we got the parabola, the circle, the ellipse, and the hyperbola are going to be our conic sections. And it's going to be very strange right now to think about this, but when it comes to conic sections, these two are actually the same thing. A circle is an ellipse, but it's got something special about the properties. A circle is an ellipse, and I'll discuss that more in the next video, in the next lecture. All right, you should probably write this down. The definition of a parabola. You've actually never seen the definition of a parabola before. Again, the conversations in the past are nothing like what we're doing today. The definition of a parabola is the set of all points in a plane that are equidistant from a fixed line and a fixed point that's not on the line. Okay, and those things have names. The fixed line, that's called the directrix. The fixed point not on the line, that's called the focal point or focus. If it's plural, when we get to ellipses and circles and hyperbolas, it'll be plural. You can call it focuses. You can call it foci, F-O-C-I. That's also a proper way of referring to plural focal points. Okay, so let me explain this. Equidistant. Okay, so here's a line down here. This is our directrix. And here's that focal point right there. Now, obviously, we can go straight down. If we do that, then equidistant means that this length is congruent to this length. There's a little bit of a term from your geometry days, congruent. But that's not the only place where we can make them congruent. They might be the shortest, but there's other places we can make them congruent. So like here, this one is the same length as this one. Now, you will notice here, it doesn't really show up in the definition, but when you do this, the angles at the directrix are always perpendicular. The only ones perpendicular to the focus is the one going through. This is the vertex. There's a term you're familiar with, the vertex of the parabola. This is not the vertex. This is the vertex. Notice the vertex, though, would be exactly halfway in between. That's actually really important to remember. The vertex will always be halfway in between the directrix and the focal point. Again, back to the term equidistant. Any of these here, if I go over to, well, actually the way I would start this is I would go perpendicular to my directrix, and then whatever that distance is there, going straight over to the focal point would end up being the same. Another comment here, notice that the focal point is, I'll call it inside. Here's my parabola here. It's inside the interior of the parabola, where the directrix is not. The directrix is outside of the interior. It's on the exterior of the parabola. That's also important to keep in mind later on, because there will be times when I will tell you, or the book will tell you in a problem, the location of the directrix and maybe the location of the focal point, but not tell you where the vertex is. Well, if you realize that this one's inside and this one's outside and then the vertex is halfway in between, it actually is telling you where the vertex is just by telling you the location of the focal point and the location of the directrix. You can surmise where that vertex is going to be. So it's important to notice that that's halfway in between and that this one's inside and this one's outside. Now I'm going to go to, let me switch this over here to a little animation I've got put together here. That's going to give us one of the interesting properties that goes with focal points. This thing here, I can actually move it a little bit. And by the way, I can demonstrate here, over here, this slider here. This is demonstrating the definition. Okay, perpendicular down here at the directrix, but they're equidistant. They're the same length, equidistant, no matter where you put them. And right there, of course, then that is right on the vertex, and it's the same distance to the focal point as directrix. So on the right side of this, I'm demonstrating one thing. Now I'm going to demonstrate something different on the left side of this. If you have a true parabola, this only happens when it's a true parabola, not with necessarily any, you can't just draw a curve at random and have this turn out to be this way. But if it's a true parabola and you've got some sort of energy source, light waves, sound waves, electromagnetic waves, coming in towards this parabolic shape, when they hit the parabola, and this could be three-dimensional, which, by the way, the term for a three-dimensional parabola is a paraboloid. This could be three-dimensional like a satellite dish in your backyard. When they hit that, they always reflect to the focal point. Now, it has to be a real parabola. Again, you can't just draw a curve on a piece of paper, winging it, and go, hey, there we go, this is a parabola. It has to match the definition. It has to fit the equations. And it doesn't matter the shape of the parabola, as long as it is a parabola, that will always occur. And here's what I mean by that. If I grab this, I can make my parabola flatter. Notice they still reflect right to that focal point. I can make it narrower, and they still reflect right to that focal point. So that doesn't matter. That's a property, a very useful property of parabolas that we're really going to be interested in, is that focal point, because there's all kinds of applications to this. If you go back to the opening pictures at the start of this lecture, you'll see I was putting lots of things where people have used the properties of parabolas in engineering applications. And a lot of these are engineering applications, I will admit that. That's mainly what we're looking at here. But in engineering applications, there's a lot of applications to a surface that reflects to a focal point. Now, it works in both ways. If you go back to that starting page, you'd see I had a light, like a headlight for a car. In that situation, as long as the reflective surface, the reflector, is a parabola, then the light source, the lamp, the light bulb, as long as it's at the focal point, when the light comes off that light bulb, it reflects off of the surface, and you get all of this going out kind of in a straight direction there. And so, again, you can change where everything is. If you change the shape of the reflector, that's fine. You just have to recalculate now where the new focal point is. And again, that's a lot of what we're doing in this unit is, okay, let's calculate where is that focal point. And so, again, just an interesting property that has a lot of applications to it. Okay, this part here I've already mentioned to you. Standard equation for a parabola. The standard of equation for a parabola can be written in one of two ways. And these two are actually the same thing here. They've just been rearranged a little bit. This is actually the one you will use most. This is called vertex form. You did see vertex form when you've talked about parabola before. If you recall, when it's in this form, that y is all by itself. And then you've got a set of parentheses here that are squared. Your vertex will be at positive h, positive k. In other words, the same sign as this one, but the opposite sign of this one. This one moves you left to right, but the opposite direction of the sign. This one moves you up or down, but the same direction of the sign. And of course, this number, if you recall, made our parabolas wider or narrower. Well, from just a second ago, what I showed you, if when they're wider or narrower, the focal point moves, then that A right there, that's going to have something to do with where the focal point's going to be. In fact, there's a formula for that. You need to write all three of these down. This is standard form of an equation. Well, actually, I think I'd like you to put this down as vertex form of a parabola. And then you've got two formulas here. And they're really the same formula. Algebraically, you can just multiply both sides by p on this one and then divide by a, and you'll get this formula here. It's really the same one. They've just been flip-flopped. It's how you're using them. Let me go to my pointer here. If you know the equation and are trying to figure out where the focal point would be, then you would want to use this version of it here. But if you know where the focal point is and you want to figure out the A for the equation, well, then you would want to use this version of it right there. It's really the same equation. It's just what is it? Now, P, I should have mentioned this, is the focal distance. Notice it's right here. P is always the focal distance, and you can measure it going from the vertex to the focal point, or because the directrix is the same distance to the vertex as the focal point, you can be told what the focal distance is there, even though we're not going to the focal point. It's the same value. These two things will be the same number. So P is your focal distance. Here's the two formulas, which it's really just one formula that you'll need for working with that. Now remember that HK gives you where the vertex is. I'm going to make a comment here because towards the end of the lecture, I'm going to do a process called completing the square. When it's in this form, it's really easy to figure out where the vertex is. It's at HK. We're going to have stuff in a different form, the general form of a quadratic, and I'm going to change it from the general form to this completed the square form. That's another name for this, or the vertex form, so that we can easily get where the vertex is. So you'll see me rearranging it to make it look like this. All right, I already mentioned reflectors. There are a ton of applications to parabolic reflectors, from headlights to, you might not know what you're looking at here. This is a solar heat collection farm. Okay, so what's going on here? There's a pipe running right down the middle there. It's got water in there, and these mirrored surfaces, this is three-dimensional parabola here, paraboloid. It's reflecting the sun from the mirrors to that pipe, which is, of course, heating up that pipe to get it really hot to the point that it can make steam. From that steam, we can turn turbines, and we can generate electricity. Now, just so you know, these things are really big. Those are some people standing right there to give you an idea of how big these things are. And we can use then that technology to, of course, generate electricity. We just need the steam to rotate the turbines. Turbines rotating will generate electricity. And there's a lot of other applications here. Here's a kind of a blow up of what's going on with that. The tube for the water would be right at the focal point, or the focal distance at least away. This is an interesting one. This was back from the Olympics a few years ago. Archimedes is the man that's given credit for this idea of a focal point on a parabolic surface. And there's a, whether it's true or not, there's a story that Archimedes used a giant mirror to reflect the energy of the sun to burn up the Roman ships as they were attacking the island that he was living on. Whether it's true or not, I don't know. I do know that in one of the Olympics, to honor him, they lit the Olympic torch by using a paraboloidish mirror here. That's what they were doing, right? This lady was lighting the Olympic torch using nothing but the power of the sun. So, kind of just a neat little application. As we go through these, let me kind of show you that there's three kind of problems that you end up running into. The first one is going to ask you to write an equation when you know a focal distance. There's different versions of this. One might be in the standard form, or this is general form. Another one might be find the focal distance. So this one we knew the focal distance, so I'm not crossing it, I'm trying to underline it. This one is find the focal distance when you do know the equation. And another one is find an equation when just given the dimensions. Okay, I'll do one of those towards the end. And then, of course, after you know that, you want to find the focal length. This here is a gigantic, it's a dish. They have it down in South America. They're listening into deep space, trying to find out if we're alone in the universe, trying to see if there's aliens out there or not. All right, so let's look at one of those kinds of problems here. Write an equation. Okay, so we've got some information here. If you look at this, we know the vertex is at 0, 0. If you just count, or you can see this, our focal distance is 2. That's the P. Now remember, P is related to A. To write the equation, and this is going to be an easy one because the vertex is at 0, 0, I don't need to mess with the H and the K. I just need the A. Well, A is 1 over 4 times the focal distance. Since I know the focal distance is -2, I should put that in there. You got to keep track of which direction these things go. The focal distance is -2. I will get a negative A then, which should make sense because this parabola is facing down. Parabolas with negative A's face down. So you just go through and you'll set it up. A is 1 over 4 times P, which is going to be a -1/8. And there's your equation right there for that particular parabola. Write an equation in standard form, or I'm calling this one standard, I guess, right now. The other one was vertex form. For a parabola with, in this case, we know where the focal point is. The focus is the focal point. We know where the directrix is. And we know where the vertex is. Now, I made a statement here. It must be facing down. How do I know that? Well, let's see. Y is at +2. The focal point is at +1. And so that's going down from where the directrix is. So it's got to be facing down. In fact, if you look at it, the vertex, again, is always halfway in between. This is lower than the directrix. This is lower than the directrix. So it's got to be facing down. Guys, these are really, really hard to do if you don't have a picture. So do yourself a huge favor. Draw yourself a picture. Here's what we do know right now. The actual shape of it, I am guessing. What do I know? I know that my line for the directrix is at 2. I know that my focal point is at 1, 1. I know that the vertex is at 1. And this is the same as 1.5. You might want to think of it as 1.5. So it's halfway in between right there. Okay. In this form, then, I know stuff. I know where the vertex is. I can plug those numbers in. The A I don't know yet, but I can figure that out pretty quick because the focal distance here would be 1/2. -1/2 because it's going down. I can put the numbers in that I know in here, and then I can simplify this until it looks like that. So I'm going to start with that. Plug in the numbers that I know after I get my A. A is 1 over 4 times P. P is a -1/2. So I end up with -1/2 for my A. Kind of a coincidence. They don't usually end up being the same thing. There, I've got it in completed the square form or vertex form. And now I need to just simplify it. So I've got all my numbers. I'm going to square this and then simplify it. So I take x minus 1 times the quantity x minus 1, and I get x squared minus 2x plus 1. I just used FOIL there, is all I did. Now I can distribute that -1/2 to each of these spots here. And then finally, I've got a squared term, I've got a first degree term, I've got a constant, I got another constant. I can go ahead and put together my like terms, and I have it in the standard or the general form of equation of a parabola. And that's what we want there. So again, the biggest hint I can give you here is draw yourself a picture. Once you get a picture, you can sort of fill these things in fairly easy. Of course, you'll have to calculate the A, but it really helps you. Notice that in our final answer, the A was negative, so it's facing down, which, yes, we already knew it was going to face down. Okay, let's go through another one. If the vertex is at the origin, so I'm going to have it right here. So again, I don't need to worry about the h and the k in this one. Find an equation for a parabola in standard form that passes through a point. Okay, so this is one with given dimensions. I know it's going through 5, 6 1/4. So over 5, up 6 1/4. After we've done that, wrote the equation, then we're supposed to figure out where the focal point is. What you want to realize here is that this is an x coordinate and this is a y coordinate. Well, I have an x in my equation and I have a y in my equation. There's nothing that says I can't just plug them in. I would know then this part, I would know this part. The only thing I wouldn't know would be the a, so that means I can solve for a. And that's going to be the plan here. Substitute in the y coordinate for y, the a coordinate for a, excuse me, x, the x coordinate for x, and then solve for a. So we'll square the 25, and we'll divide, and we'll get the a. Now that we know the a, we can write the equation. There's your equation right there. Last thing is, where would the focal point be? Now it should be up. Okay, it's inside. We know what a is, and the focal distance equals 1 over 4 times a. So 1 over 4 times 0.25, and that's going to give us actually just 1. So our focal point is going to be right there. And that's how you do one with dimensions. In other words, giving information about where a point is. Just remember, you can just plug it right into the equation. Okay, finding a focal point. This is with a satellite dish here. This is called the feed horn. Of course, this is applying the properties here. Those signals are coming from space so you can watch your TV shows. They hit this, they reflect straight to where the receiver's at on that feed horn. And so you're getting all of that information coming in here, bouncing right to that part there. Okay, so we got to figure out where should that be. If we know the dimensions of this, then where should the focal point be? So the dimensions, this receiver here is 47 centimeters across. This is an audio one actually that I'm working with here. This would be like what you would see in an NFL football game. You might see a guy on the sidelines holding this contraption with a microphone on it so that you can hear people talking out on the field. That's what this one is. It's 47 centimeters across, 5 centimeters deep. Okay, so 5 centimeters deep right here. So what we're talking about, how far from the bottom of the dish, and we'll assume that the vertex is at the bottom of the dish, how far from there to where the receiver should be. So really just focal distance is what I'm trying to figure out here. I'm going to redraw this. It's a little bit easier to see here. So 47 all the way across. Now the vertex I'm just because I get to choose, I'm going to place it right at 0, 0. Half of the 47 is 23.5. That's where this number is coming from. What I'm doing is real similar to that last one. I'm figuring out a spot on the parabola. If it's 5 centimeters deep here, well, then I know that this is 5 centimeters up to get to here. I know that outside corner. I'm working off my corner right there, where that's going to be, and I know these values. Again, there's an x, there's a y. Hey, I can just plug them right in, and in fact, that's what I've got right here. There's my y, there's my x, quantity squared. I can solve for a at this point, just using my equation there. I end up with a is equal to 0.00905. And so then I can go from there to solve for my focal distance. Remember, that was the question. I was trying to figure out what's the focal distance. Well, it's 1 over 4 times a. So 1 over 4 times that. 27.6 centimeters should be where that receiver is placed. Of course, any closer, any farther away is not going to work as well. Okay, let's find the vertex and focus of a parabola, and then we're going to sketch it. Okay, so here I've got this equation here. This is helpful if I can have it like that. In other words, or at least I have the y maybe by itself. Usually we actually put the k over here. So what I'm going to do is I'm going to put the x squared on the other side, and then I'm going to divide by the 6. And I do make a comment there. At this point, we know that 0, 0 should be on it, because if you plug in 0 to both of these, well, it makes the equation true, so that should be on it. Well, let's divide by 6. There we go. Y is equal to negative 1/6 x squared. All right, we've got our formula. We've already figured out where the vertex is. The focus. Well, we've got the A. As soon as we get the A, we can solve for the focal distance P. P is 1 over 4 times A, so I just got to go 1 over 4 times a negative 1/6. And what I end up with is a focal distance of negative 1.5. So right about there is where that focal point is going to be. And there it is. By the way, the directrix was 1.5 back as well. All right, completing the square. When it's in this form, I've been mentioning it, when it's like this, it's really easy to figure out where the vertex is. It's something called vertex form, or I've been actually slipping in there today, completed the square form, because it's also called that. So notice I need a parentheses with something inside being squared, something else out here, and maybe a number out there. If there's nothing there, we assume it's a 1. Well, this isn't really anything like that. The process goes like this. First of all, if you've got a number in front of your x squared term that's anything but a 1, you're going to have to factor. Now, you'll factor from both terms that have x's. You do not need to factor from this, and I would recommend that you don't, because you're just making a fraction for yourself where you don't need to mess with one. But you do need to factor from these two. So you're going to see that I'm going to have done that. There we go. I factored out that 3. Now, the next part of the process goes like this. What I'm going to do is I'm going to take whatever this number is here. I'm going to cut it in half. In this case, it'd be a 1. In fact, I'm going to put +1 here just to remind me if that sign is different. If this was a negative, I would keep the sign. But it's not, so I'm just going to put a 1 right there. Okay, I guess I kind of double did that. And then I'm going to take the number and I'm going to square it. And there it is right there. Now realize I just threw a number into my equation out of thin air. I just looked at it, said, this is what I'm going to do, and I plugged it in. Well, I hope that your math instincts was screaming that you should not do that. And you're right, you can't just do that unless you balance out the fact that you just threw a number into the equation. Now, if this negative 3 wasn't here, I would say this. I'd say, hey, we just added 1, so let's subtract 1. But I'm doing one that's a little bit more complicated here, because when we put this here, pretend we distributed this negative 3. You'd have a negative 3 here, which means when I put that in there, I actually put in a negative 3 in, which means to balance out the fact that I just threw a negative 3 in, I need to throw a positive 3. But I'm going to put it over here, not inside. The reason I'm doing this is because now you're not going to notice this till I'm done here, but this part here, that is a perfect square. A perfect square is anytime you multiply something by itself. It's the result of a perfect square. What is it? Well, if you were to factor this, it would factor into x plus 1 times x plus 1, which is x plus 1 quantity squared. Something times itself. It's a perfect square. How do I know it's x plus 1? Well, the truth is I don't actually factor it. I know that if I did factor it, that's what I'd get. But it's always this number right here. That's why I write it down. It's going to be x, and then whatever the sign is, and then whatever the number is, quantity squared, is just going to be what it is. If you want to take time and factor it, you go ahead, have fun. It'll factor into x plus 1 times x plus 1. Otherwise, just use my little trick here. It's going to be that number. Goes right in there. The 3 comes along. Here I simplify. And notice, it's in completed the square or vertex form. Now I know things. I know that my vertex is at negative 1, 5. I know the A, so from the A I can calculate the focal distance P. And we're practically done with this thing. There's your focal distance. And so we know where the focal point is. And we know where the directrix is. I'm getting the 1, 5 plus. Okay, so I'm just taking these negative 1 and the 5, and I'm adding and subtracting 1 12th. That's what I did there if you're wondering how I came up with that. If that's kind of confusing, draw yourself a picture. You know where the vertex is. The vertex is at -1, 5. So over 1, up 5. Okay, there's the vertex. From that, you're going down a 12th to get to the focal point. So you'd have to go 5, take away a 12th. That's where I'm coming up with this 59 twelfths. And it's over -1. So pictures will help you think your way through this. And then the directrix is it's the focal distance, behind it. So I added a 12th, which is 61 twelfths. All right, there's some problems to take a look at. Have a good day.